Hello friends, welcome to a lecture series on matrix analysis with applications. So, in the first lecture we have seen that how we can apply elementary row operation to get a row equivalent form of a matrix A. Okay. Now, we will see echelon form of a matrix. What do you mean by echelon form and how we can obtain echelon form by applying elementary row operations. Before starting echelon form, we will see elementary matrices. What do you mean by elementary matrices? An n cross n square matrix is called an elementary matrix E if it can be obtained from n cross n identity matrix I n using a single elementary row operations. We have already seen the last lecture that there are three basic elementary row operations. The first is you replace any row by multiplying it by a non-zero scalar. The second elementary row operation is you replace any row r say rth row by rth row plus c times some sth row, okay, and you can always interchange any two rows. So, these are the basic three elementary row operations. Now, if you apply an elementary row operation in many matrix A and the same elementary row operation you apply in the identity matrix I, then that matrix which is obtained from I is called an elementary matrix. Okay. Now, the elementary matrix said to be of type 1, 2 or 3 according to whether the elementary operation performed on I n is a type 1, 2 or 3 operation respectively. The three operations which we have defined, if we are applying the first operation of the identity matrix, we are saying it is a elementary matrix of type 1, similarly type 2 and type 3. Now, for example, interchanging the first two rows of I 3 produces the elementary matrices this. You see, if your identity matrix and you interchange first two rows, so this matrix is obtained and this matrix we call as elementary matrix. Okay. Now, this is a result, let A is a m cross n matrices over the field F, and suppose that B is obtained from A by performing an elementary row operation. Okay. Then there exists an m cross m elementary matrix E such that B is equal to E A. So, there always exists an elementary matrix E such that B is equal to E A. In fact, E is obtained from I m by performing the same elementary row operation as that what was performed on A to obtain B. Okay. If you obtain B from A by applying some elementary row operation and same elementary row operation you applied on I m, so we obtain E. Conversely, if E is an elementary m cross m matrix, then E A is the matrix obtained from A by performing the same elementary row operation as that which produce E from I m. So, converse of the statement is also true. So, let us discuss it by a few examples. See, you have matrix A here. A is this matrix of order, you see it is 3 cross 4, 3 rows 4 columns. Now, in this matrix you suppose interchange the second row of A with the first row, you apply elementary row operation, you interchange R 2 by R 1. So, the new matrix is obtained which is row equivalent to A, which is 2 1 minus 1 3, the second row. The first row will be in second row now 1 2 3 4 4 0 1 2. Okay. And if you have an identity matrix, okay, here is order 3 cross 3 and you interchange the first and the second row. So, this matrix is obtained and this matrix is an elementary matrix here, okay, and E A is always equal to B. When you multiply E with A, this E with A, then you easily obtain B. this you can easily check. Okay. Now, let us take second example. You see, here A is this matrix. Okay. Now, suppose we want to transform this A into I by applying elementary row operations. Okay. Then, now how you will make this as an identity matrix? By applying elementary row operations. You see, the first element is 1 here, which is a non-zero element. You first interchange this row with the first row, that is, you interchange R2 and R1, you will obtain a new matrix B1, which is 1 0 minus 1. This row will come here and this row will come here 0 1 0 and this 4 0 1. Now, you make 0 here with the help of this. So, this minus 4 times this. So, replace R3 by R3 minus 4 times R1. You get new matrix B2 and B2 will be equal to, the first 2 rows remain the same, and the third row, this minus 4 times this will be 0, this minus 4 times this will be 0, this minus 4 times this will be 5. Now, you make 1 here. To make 1 here, you would simply divide this row by 5. You obtained this matrix B3, which is 1 0 minus 1 0 1 0 0 0 1. Now, to complete identity, you have to make 0 here with the help of this. So, this plus this, that is, you replace R1 by R1 plus R3. So, this will give an identity matrix B. Okay. Now, to obtain this matrix, from this matrix, what is the elementary matrix? You see, we have interchange R2 by R1. So, same elementary row operation you apply on identity matrix of order 3 cross 3. You replace R2 by R1. So, which matrix we will obtain? The matrix which will obtained as this matrix E1 0 1 0 1 0 0 0 0 1, which is obtained by interchanging R2 and R1 of identity matrix. Okay. Now, similarly to obtain B2 from B1, we have done? We have replaced R3 by R3 minus 4 times R1. Now, you apply same elementary row operation in the identity matrix to get the new elementary matrix E2. Okay. So, here if you take the identity matrix and replace the third row by third row minus 4 times the first row, then you get minus 4 0 1. So, this will be elementary matrix 2. Similarly, now you take the third B3. How B3 is obtained from B2? To obtain B3 from B2, you have divide simply the third row by 5. You apply the same elementary row operation in the identity matrix to get the elementary matrix corresponding to this row operation. So, what will be that? You simply divide the third row by 5. All the 2 rows are same. So, this is E3. And similarly, the E4 can be obtained by simply adding the first row by the third row. The same, you apply the same elementary row operation in the identity matrix. You apply the same elementary row operation identity matrix to get E4. Now by the theorem which we have just stated, to get B1 from A, we have the elementary row operation E1. Okay. So, this can be written as, B1 can be written as E1 times A, because E1 is the elementary matrix corresponding to this row operation. Similarly, B2 will be E2 into B1, B3 will be E3 into B2, and similarly the last matrix B, which is an identity matrix of course, is E4 into B3. Now, what we have obtained, if you substitute B3 over here, substitute B3 here, this is E3 into B2. Okay. Then you replace B2 by E2 into B1 and then B1 by E1 into A. So, what finally we have obtained? Finally, we have obtained B is equals to E4, E3, E2, E1 into A. Okay. So, that means if here we have applied 4 number of elementary row operations, and for each elementary row operation we obtained an elementary matrix. Okay. To get the final matrix, which is a row equivalent to a matrix A, okay, they simply E4 into E3 into E2 into E1 and the first matrix, initial matrix A. Okay. Or we can say that B equal to EA, where E is simply multiplication of all elementary matrices. in this order E4, E3, E2, E1. So, that means what I want to say that if any M cross N matrix A is transformed to B by applying k number of elementary row operations, then there exists an M cross M invertible square matrix U that is a product of elementary matrices U equal to Ek minus 1, Ek minus 2 up to E1 such that B is equals to U into A. Okay. So, that matrix always exists and it is invertible. And why elementary matrices are invertible? You see, elementary matrices are obtained from identity matrix by applying some elementary row operations, and applying elementary row operation, you see if you see a matrix A, you apply some elementary row operation on this matrix, elementary row operation, and you got a new matrix B which is a row equivalent to A. Okay. So, this matrix can be obtained either by interchanging two rows or to multiply this A by any row of this matrix A by a non-zero scalar, or you replace some ith row by ith plus C times jth row where I not equal to j. Okay. So, we can simply say that determinant of A will be some alpha time determinant of B, where alpha is not equal to 0, because applying elementary row operation will not change the nature of the matrix. I mean, if it is invertible, remains invertible. Okay. It simply change the determinant of the matrix by some scalar, because we can multiply a row by a non-zero scalar. So, elementary matrices are obtained from identity matrix by applying elementary row operations. So, since identity matrix is invertible, it has a determinant 1. So, elementary matrices are also invertible, because determinant of identity matrix will be some alpha time determinant of E, where alpha is not equal to 0 and E this is 1. So, this implies determinant of E is not equal to 0. Okay. So, elementary matrices are always invertible. Okay. And then their product also invertible, because product of invertible matrix is also invertible. Okay. Now, come to echelon form of a matrix. A matrix A is called an echelon form or is said to be an echelon form if the following two conditions hold, where a leading non-zero element of a row of A is the first non-zero element on the row. Okay. We are taking the leading element as the first non-zero element in that row. Okay. So, what are two properties? The first property is all 0 rows, if any, are at a bottom of the matrix. If there is a row containing all zeros, that must be at the bottom of the matrix, number 1. Number 2, each leading non-zero entry in a row, leading non-zero entry means the first non-zero entry in a row is to the right of the leading non-zero entry in the preceding row. If you have the second row, the first non-zero entry in the second row must be on the right side of the first non-zero entry in the first row. Okay. That is, if rows are 1, 2 up to R are the non-zero rows of a matrix, and if the leading non-zero entry I occurs in the column Ki, I from 1 to R, then K1 is less than K2 is less than Kr. So, let us discuss this by some examples. Now, you see here, now you focus on the first matrix. You see, first of all the 0 rows are at the bottom. The row containing all 0 elements is in the bottom, the first property holds. Now, you see the first leading element, leading means the first non-zero element is here, this is A12. The first leading non-zero entry here is this one, the first non-zero entry here is this one. Now, this element, the first non-zero entry of this row is to the right of this row. the first non-zero entry of this is to right of this row, the next row, okay, right of this row. So, this satisfy the properties of the echelon form of a matrix, and hence we can say that this is an echelon form. Now, if you see second example, the second example you see that there is no row containing all 0. Okay. Now, this is the first non-zero element in this row, this is the second non-zero element in this is the first non-zero element in the second row, and this is this is the non-zero element in a third row, and all the non-zero rows, this non-zero, this leading element of this row is the right of this leading element of this row is to right of this. So, this is an echelon form, this is a echelon form of some matrix. However, if you see here, you see this is not an echelon form, because this row is containing all 0 element, but it is not at a bottom of the matrix. So, this is not an echelon form. Here if you see in this example, this is the first non-zero element of the first row, and this is the first non-zero element of the second row, but this non-zero element is on the left of the first non-zero element of the preceding row. So, this is not an echelon form, because it must be on the right side. If it is 0, then we have to make 0 here to make it an echelon form. Okay. So, this is not an echelon form. Now, let us try this example, that how we can make it an echelon form of the matrix. So, what is the problem? Problem is 1, it is minus 3 2, then it is minus 4 0 5. Now, suppose by applying elementary row transformation you want to find out its echelon form. So, the first non-zero element 1, we leave it as it is. Now in this row, to keep all the non-zero entries on the right, you see if we have in the echelon form, each leading non-zero entry is to the right compared to the preceding row. Okay. To satisfy that condition, you take the first non-zero element in the first row and make 0 below in that column, all the elements must be 0 in that column. Okay. So, you apply elementary row operation to make 0 here, you take R2 and replace R2 by R2 plus 4 times R1. If you make this elementary row operation, it is minus 1 3 2, it is 0. Now, it is this plus 4 times this is minus 12, this plus 4 times this is 13. Okay. Now, this is the first non-zero element of this row, which is 1. This is the first non-zero element of second row, which is minus 12, and it is to the right of this row. There is no row containing all the 0 elements. So, we can say that this is the echelon form of this matrix A. Okay. So, in this way we can convert we can find out the echelon form of a matrix. Now, let us consider second example. The second example can be framed. You see, we have to form the echelon form of this matrix. So, how we can do that? Now, what is the matrix now? The matrix is, it is 2 4 minus 3 minus 2. Then it is minus 2 minus 3 2 minus 5. One 3 minus 2 2. Now, you want to frame its echelon form. So, you leave first non-zero element as it is, make 0 here with the help of this, make 0 here with the help of this. So, you apply elementary row operations. So, you replace R2 by R2 plus R1. So, this is 2 4 minus 3 minus 2, it is 0, it is 1, it is minus 1, it is minus 7. You leave it as it is, the third row you leave as it is. Now, you make 0 here with the help of this. So, you take R3 by R3 minus 1 by 2 1 by 2 R1. Okay. So, it is 2 4 minus 3 minus 2, it is 0, 1, minus 1, minus 7, it is 0, it is 3 minus 2 is 1, then it is minus 2 and it is plus 3 by 2, that is minus 1 by 2, then it is 2 plus 1, that is 2 plus 1 is 3. Okay. Now this is okay, and this is to right of this side. Now below this element make all the elements 0. Okay. You pick out the first non-leading element, make 0 in that column, leaving this element make 0 to all the elements below this, and the second non-zero second leading element, I mean second non-zero element in that column, in that row, make 0 below. Okay. So, here you make 0, you simply replace R 3 by R 3 minus R 2. So, this will be simply 2 4 minus 3 minus 2, this is 0 1 minus 1 minus 7, this is 0 0, this is 1 by 2, and this is 10. Okay. So, this is okay and this is okay. Now, yeah, now it is okay. You see that there is no row containing all 0, and all the if you take this first non-zero row, this first non-zero entry, all the elements below this are 0, first non-zero entry second row, all the elements below this are 0 and their third element. So, this is the echelon form of this matrix. Okay. So, this is all about echelon form. We will see some more illustrations of echelon form and its applications in the next lecture. Thank you.